In the span of 9 days this year, the ground opened in 4 different countries. A fishing village on the Pacific felt its walls crack at 3 a.m. A city of 2 million people watched its bridges sway for 11 seconds. None of these places shared a fault line, a plate boundary, or a single obvious cause. Thousands of miles apart, a seismologist in a quiet monitoring station noticed something in the data that shouldn't have been there. On 2 separate machines, on 2 separate continents, the needles jumped in the exact same instant. Not similar, identical. She checked the equipment. She checked it again. Nothing was broken, and nothing about it made sense yet. But to understand why those needles moved together, you first have to understand that the ground you trust has never once been still. The restless year. Since January, seismic networks have logged over 190 earthquakes of magnitude 6 or higher, a pace well above the planet's yearly average. Papua New Guinea felt 3 major ruptures in a single week. Weeks later, a swarm beneath the Santorini Strait in Greece produced more than 20,000 individual tremors in less than 2 months, most too small to feel, but enough to empty a resort island of its residents. Alaska, Ecuador, and the Kuril Islands each logged significant quakes within days of one another, scattered across 3 different oceans with no shared trigger that anyone could point to. Seismologists who track this for a living started comparing notes because the clustering looked less like coincidence and more like rhythm. No single fault caused it. No single region owns this year. Yet the shaking itself is the oldest story this planet has ever told. And to read it, you must go back to the beginning. A planet that moves. Imagine you're floating a few hundred miles above the Earth, far enough that the oceans look like glass and the continents look painted on. From here, nothing moves. The planet looks finished, permanent, done. But hold that view for a few million years, just a blink in Earth's 4.5 billion year life, and the illusion falls apart. The continents drift. Oceans widen by a few centimeters a year, roughly the speed your fingernails grow, and mountain ranges rise like slow waves frozen mid-break. The Earth has never been the fixed, solid thing it appears to be from a photograph. It is closer to a held breath, always shifting, always adjusting, on a timescale too slow for any human life to notice. That motion is gentle now, but it began with a single crack that has never fully healed. The first tremor. Long before anyone measured a tremor, they felt it, and they tried to make sense of it the only way they knew how. In Japan, storytellers spoke of a giant catfish sleeping beneath the islands, pinned down by a god with a stone. When the catfish stirred, the ground cracked open. In Greece, they blamed Poseidon striking the earth with his trident when he was angered. In Mesoamerica, some believed the world rested on the shoulders of a being who occasionally shifted its weight. Every culture built its own monster, its own god, its own reason for the shaking, because an explanation, even a false one, was easier to live with than silence. These weren't foolish guesses. They were the earliest attempts at cause and effect, reaching for a hidden mechanism no one could see. Their gods and beasts were wrong, but the terror they felt pointed at something real buried far below. Signals in the night. Right now, as you sit still, the ground beneath you is moving. Not the shaking that makes headlines, but something quieter. A constant hum of tiny tremors passing through rock, water, and soil every hour of every day. Most are so faint a human body could never register them. They start deep, sometimes hundreds of kilometers down, where heat and pressure bend solid stone as if it were taffy. The energy ripples outward in waves, some racing through the planet's interior, others creeping along its surface, fading long before they ever reach the air we breathe. For most of history, these signals pass completely unnoticed, whispers with no one listening. Someone had to learn to listen to those whispers and the story of how we did is stranger than the quakes themselves. The Watchers. The first real attempt came in 132 CE, when a Chinese scholar named Zhang Heng built a bronze vessel ringed with dragons, each holding a ball in its mouth. When a tremor passed, however faint, a ball would drop into the mouth of a waiting bronze toad, marking the direction the shock had come from. It would be nearly 1-800 years before anyone improved on the idea in any meaningful way. In the 1800s, scientists in Italy and Japan began building pendulums and levers sensitive enough to trace the ground's faintest motion onto smoked paper and rotating drums. They called this new science seismology, the study of shaking, and for the first time, humans had a way to record what they could not feel. Their crude machines revealed a truth so unsettling it changed what we thought the Earth even was. The old fear. For thousands of years, every culture that built cities near fault lines learned the same lesson. The ground could open, buildings could fall, entire populations could vanish in minutes. Pompeii buried under ash in 79 AD. Lisbon shattered in 1755, killing 60,000 in 6 minutes. Port Royal sinking into the sea in 1692, swallowed by liquefied sand. The earth wasn't stable, it wasn't safe, and no prayer, no offering, no act of devotion could stop it from shaking when it wanted to. That fear made sense once, but the real danger was never where anyone was looking. Beneath your feet. Imagine standing on solid ground. Now imagine descending. The first few meters are soil and rock, compressed sediment laid down over millennia. Go deeper. 10 kilometers down, the temperature climbs past 200 degrees Celsius. The rock is hot enough to glow faint red, squeezed under pressures that would crush steel. At 35 kilometers, you pass through the bottom of the crust into the mantle, a zone of rock so hot it flows like thick honey over geological time. It's not liquid, not solid, but something in between. By 100 kilometers, the temperature hits 1,400 degrees Celsius. By 2,900 kilometers, you reach the outer core, molten iron spinning in slow currents that generate Earth's magnetic field. The deeper you go, the more you realize the surface is only the thinner skin over something enormous. The broken shell. The crust isn't one unbroken shell. It's fractured into 15 major pieces and dozens of smaller ones, each drifting across the surface at speeds measured in centimeters per year. The Pacific plate moves northwest at 7 centimeters annually. The North American plate inches west at 2.5 centimeters. The African plate splits apart along the East African rift at 6 millimeters per year. These plates don't glide smoothly. They grind, collide, dive beneath one another. Where they meet, the crust buckles into mountains or tears open into ocean trenches 11 kilometers deep. Each plate weighs trillions of tons. They carry continents, oceans, entire ecosystems on their backs as they crawl across the mantle. Something has to push these vast plates, and the source of that push is the whole secret. Rivers of stone. Deep beneath the crust, the mantle churns. It's not liquid like water, not solid like rock. It flows like glass heated until it bends, creeping upward in some places, sinking in others, turning over in cycles that last millions of years. Picture vast columns of stone, glowing orange in the darkness, rising from depths of 2,900 kilometers. They move at the speed your fingernails grow, maybe 5 centimeters a year. Where they reach the underside of the crust, they spread sideways, dragging the plates above them like rafts on an impossibly slow current. This is convection, the same process that makes water boil, but stretched across geologic time. Hot mantle rises, cools, sinks back down. The cycle never stops. It's been turning since the Earth was young, driving the plates, building mountains, tearing continents apart. This molten current moves too slowly to see, but its rhythm may be the reason the whole planet is shaking now. The slow drift. The continents don't stay put. Africa is splitting along the East African Rift at 7 millimetres per year. The Atlantic widens as Europe and North America drift apart at 2.5 centimetres annually. Australia races north toward Asia at 7 centimetres a year, the fastest moving continent on Earth. Over 200 million years, Pangaea tore itself into the map we know today. In another 250 million, the continents will gather again into a new supercontinent, perhaps around the Arctic or swallowing the Pacific entirely. The dance is endless and inevitable. Every millimetre of motion bends the rock at the plate edges. The stress accumulates silently, invisibly. A fault that slips 4 centimetres a year stores decades of energy in a single, locked section. That energy waits in the stone, elastic deformation building year after year. All that stored pressure has to go somewhere, and where it goes is where the danger begins. Where plates meet. The boundaries are where the violence happens. At divergent margins, plates pull apart and magma wells up to fill the gap. At transform faults, they grind past each other horizontally, the friction screaming through the rock. At convergent zones, one plate dives beneath another, plunging back into the mantle in a process called subduction. Subduction zones produce the planet's largest quakes. The Cascadia Zone off the Pacific Northwest, the Japan Trench, the Peru-Chile Trench. These are the places where an entire tectonic plate bends and slides beneath its neighbour, sinking at 8 centimetres per year, 10 centimetres, sometimes more. The descending slab drags everything down with it, and when it catches, when friction locks the boundary in place, centuries of motion compress into seconds. 90% of all earthquakes occur at plate boundaries. The pattern is so reliable that seismologists map the edges of plates simply by plotting where the ground shakes. The boundaries light up like neon signs on a global map, tracing the Ring of Fire, the Mid-Atlantic Ridge, the Himalayas where India still crushes into Asia. Most quakes are born at these seams, but the ones baffling scientists were not. The Ring of Fire. The Ring of Fire is a horseshoe of violence wrapping 25,000 miles around the Pacific. 90% of the world's earthquakes happen here, where the Pacific plate dives beneath a dozen neighbours, grinding into the mantle at 3 inches per year. Japan, Indonesia, Chile, Alaska, all of them built on fractures that never rest. In a single year, magnitude 6 quakes strike the ring dozens of times. Magnitude 7s arrive every few months. The seafloor buckles, cities sway, and the pattern repeats because the geometry demands it. Subduction zones don't sleep. Seismometers along the ring record a constant hum, background tremors too small to feel, but never absent. The crust here is always failing, always slipping, always releasing the stress that tectonic collision builds. You'd expect the ring to roar, but the tremors that broke the pattern came from places that should be quiet. The silent faults. A silent fault is a fault that hasn't moved in living memory. The rock on either side presses together, friction locking them in place while stress accumulates year after year. No tremors, no warnings, just stillness that can last centuries. The New Madrid Fault in Missouri last ruptured in 1812, tearing the ground so violently that the Mississippi River flowed backward. Since then, nothing. The fault sits in the middle of a stable continent, far from any plate boundary, storing energy in perfect calm. Geologists know it will break again, they just can't say when. Silent faults exist on every continent. Some haven't moved in 2,000 years. The longer the silence, the larger the eventual rupture, because the stress never stops building. In 2023, researchers began cataloguing faults that had been dormant for at least 500 years. A silent fault can wait 1,000 years, so what convinced so many to stir at once? A question of timing. Between February and August 2023, 14 magnitude 6 or larger earthquakes struck regions classified as low activity zones. That's more than double the historical average for those areas in a single year. Turkey, Morocco, Afghanistan, all far from major subduction zones, all within 6 months. Seismologists expect randomness. Quakes don't follow schedules and clusters happen by chance. But when you map the 2023 events by date, the intervals are tight, almost rhythmic. 1 every 18 days on average, scattered across 3 continents with no tectonic link between them. The spatial distribution was wrong. The timing was worse. If faults rupture when stress exceeds rock strength and stress accumulates over decades, why would unconnected faults thousands of miles apart reach failure within weeks of each other? Timing is where the mystery sharpens, because coincidences this large tend not to be coincidences at all. The cluster. In April 2012, 2 magnitude 8.6 and 8.2 quakes struck off Sumatra within 2 hours. 11 days later, a 7.0 in Mexico. 3 days after that, a 6.9 in Indonesia. By the end of that month, seismologists had logged a spike in large earthquakes that exceeded the yearly average for decades prior. The spacing wasn't random. Faults that hadn't moved in centuries woke up within weeks of each other, scattered across the Pacific, the Indian Ocean, the Americas. Statistically, the chance of that many major quakes clustering so tightly in time hovers near improbable. You could call it a fluke, except it keeps happening. 2015 saw another surge, 2018 another. The intervals are too short, the distances too vast, the timing too precise. If they were connected, then something had to carry the signal between them across the entire globe. Echoes. Across oceans. When a fault ruptures, it doesn't just shake the ground nearby. It sends seismic waves radiating outward in all directions, some travelling through the planet's interior, others rippling along the surface at 4 kilometres per second. Within minutes, instruments in Antarctica can detect a quake that began in Alaska. Surface waves circle the Earth multiple times, ringing the planet like a bell. The 2011 Tohoku quake in Japan sent waves that were still measurable after 5 complete passes around the globe, each lap taking roughly 3.5 hours. Every seismometer on Earth recorded it. For decades, those waves were treated as echoes, useful for mapping Earth's interior, but otherwise inert. Then researchers noticed something strange. In the hours after a great quake, smaller tremors would ignite thousands of miles away. In places, the main shock's ground motion should have been too weak to matter. These waves don't just record earthquakes. Under the right conditions, they may cause them. The distant trigger. It's called dynamic triggering. A magnitude 7.9 in Alaska sends surface waves through Yellowstone, and suddenly the geysers there erupt out of sequence. A magnitude 9.1 in Sumatra nudges faults in Nevada into motion 16 hours later, 12,900 kilometres away. The passing wave doesn't need to be violent. Amplitudes smaller than the rumble of a passing truck have been enough. The mechanism is delicate. Faults already near failure, loaded with decades of stress, can be tipped over the edge by a transient jiggle lasting seconds. It's not the wave's strength, but its timing, the way it tugs at a fault already primed to slip. Seismologists have documented dozens of cases since the early 2000s, each one confirming the same unsettling truth. Earthquakes can reach across oceans. But dynamic triggering mostly affects shallow faults, the ones within 15 kilometres of the surface. The waves lose energy as they travel, and they can't explain quakes deeper than that, or clusters separated by weeks instead of hours. One quake waking another across an ocean is astonishing, but it's still only the surface of the answer. Something deeper. So if the trigger isn't just waves rippling across the surface, where does it come from? Some researchers started looking down instead of sideways, past the crust, past the upper mantle, toward a boundary we've never seen and never touched. We've drilled 12 kilometres into the Earth at most. The distance to the centre is over 6,300 kilometres. Everything below that thin scratch we've made is inferred, not observed, pieced together from the way sound moves through rock we'll never hold in our hands. And yet the patterns keep pointing downward. Quakes that shouldn't be connected, connected. Timing that shouldn't align, aligning. To reach it, scientists had to stop studying the surface and start listening to the heart of the world. The deep quakes. Picture a fault line 600 kilometres down. At that depth, the pressure is crushing over 200,000 times what you feel at sea level. Rock under that kind of squeeze doesn't crack, it bends. It should flow like thick tar, not snap like glass. But it does snap. Seismographs pick up sudden, sharp ruptures as deep as 700 kilometres, the same signature as a shallow quake, just buried far beyond where breaking is supposed to be possible. For decades, this sat as an open contradiction in geology, a phenomenon with a name, deep focus earthquakes, but no accepted cause. Rock that deep shouldn't snap at all, and the reason it does upends everything you assumed about the ground. Below the crust. Start the descent slowly. Beneath the crust, roughly 100 kilometres down, you enter the upper mantle, and the rock here already behaves like nothing on the surface. It's solid, but it moves. Over millions of years it creeps, folds and circulates like something closer to liquid. Geologists call part of this layer the asthenosphere, from a Greek word meaning without strength. It's still mineral rock, still technically solid, but soft enough that entire slabs of crust ride on top of it, drifting inches a year, like rafts on a barely moving current. It's a strange in-between state, not molten, not rigid, something the surface world has no real equivalent for. This layer flows and fractures at once, but it's still just the doorway to something far stranger below. The mantle's secret. Deep inside that yielding layer, something extraordinary happens. Columns of superheated rock rise from the depths, pushed upward by heat that has nowhere else to go. They climb through thousands of kilometres of mantle, narrow pipes of material hundreds of degrees hotter than everything around them. When they reach the crust, they burn through. Hawaii sits over one, Iceland straddles another, Yellowstone rests on a third. These mantle plumes punch through tectonic plates like welding torches through sheet metal, creating volcanoes in places that have no business hosting them, thousands of kilometres from any plate boundary. The plumes feed a slow churn that reshapes the entire mantle over tens of millions of years. Hot material rises, spreads sideways beneath the crust, cools, and sinks back down. It's a cycle measured in epochs, a conveyor belt operating on geological time, dragging the continents with it as it turns. These deep currents shape whole continents, yet even they answer to a force deeper still. Heat from within. The heat driving that immense circulation comes from two sources. The first is primordial, left over from Earth's violent birth 4.5 billion years ago. When the planet coalesced from dust and rock, the collisions generated staggering amounts of energy. That heat never fully escaped. The second source is decay. Deep in the mantle, radioactive isotopes break down one atom at a time. Uranium-238, thorium-232, potassium-40. Each decay releases a tiny burst of energy, and there are trillions upon trillions of them happening every second. A steady furnace burning on the timescale of half-lives measured in billions of years. Together, these sources keep the mantle at temperatures between 1,000 degrees Celsius and 3,700 degrees Celsius. But the primordial heat is leaking away through the crust, and the radioactive fuel is slowly depleting. Earth is cooling degree by imperceptible degree, on a timeline so vast it makes human history look like a single frame in an infinite film. That heat is the engine of everything, and one day it will fade, but not before it does something remarkable. The convecting sea. Picture the mantle as a vast ocean, 2,900 kilometres deep, heated from below and cooled from above. Hot rock rises where the heat is strongest, spreads outward as it reaches the underside of the crust, loses energy to the surface, and sinks back down where it cools. The entire layer turns over in enormous loops, each cycle taking 50 million to 200 million years to complete. This is mantle convection, the engine that drives plate tectonics. Where the hot material rises, it pushes continents apart and creates new ocean floor. Where the cold material sinks, it drags plates down into subduction zones, triggering earthquakes and volcanoes. The crust is just a passenger, carried along by currents it can't resist. The convection cells aren't uniform. Some are massive, spanning half a hemisphere. Others are smaller, regional, nested inside the larger flows like eddies in a stream. They interact, merge, split apart, creating a shifting three-dimensional landscape of motion that determines where every earthquake will strike, where every mountain range will rise. Something has to keep this vast sea boiling, and that something lies at the very centre. The cooling world. Earth began its life as a ball of molten rock 4.5 billion years ago, glowing bright enough to light the early solar system. Since that first moment, it has been cooling, radiating heat into the void degree by degree, century by century. The process is almost unbearably slow. The mantle loses perhaps 50 degrees Celsius every billion years. As the planet cools, it contracts, shrinking by fractions of a millimetre each year. The crust fractures to accommodate the change. Mountains fold inward. Ocean floors buckle. The entire rocky shell adjusts to fit a world that is imperceptibly smaller than it was the day before. Most of this heat escapes silently through the seafloor, carried away by black smoke events and slow diffusion through ancient stone. But some is trapped, building pressure in pockets and weak zones until the rock can no longer hold. Then it moves suddenly, violently, in a release we call an earthquake. A cooling planet is a restless one, and its restlessness may be entering a new phase. The iron heart. Beneath the mantle lies something stranger still. At 2,900 kilometres down the rock gives way to liquid metal, an ocean of molten iron and nickel spinning in the darkness. This is the outer core, a sea 2,300 kilometres deep, where temperatures reach 4,400 degrees Celsius and pressures crush matter into forms unknown at the surface. The metal churns in vast, slow currents driven by the planet's rotation and the cooling of the inner core below. As it moves, it drags magnetic field lines with it, twisting and stretching them into loops and spirals. This dynamo generates Earth's magnetic field, the invisible shield that deflects solar wind and makes compasses point north. But the field is not constant. It weakens and strengthens over decades. Its poles wander across the Arctic and Antarctic, and every few 100,000 years it flips entirely. Magnetic north becomes south. These changes reflect shifts in the flow patterns deep below, eddies and waves propagating through the metal sea. This metal sea powers far more than a compass, and its restlessness reaches all the way to the surface. The inner sphere, at the very centre, 5,850 kilometres beneath your feet, floats a sphere of solid iron 1,220 kilometres across. This is the inner core, crystallised from the liquid metal around it by pressures 3.6 million times greater than the air you breathe. Its surface temperature is roughly 5,200 degrees Celsius, hotter than the visible face of the sun. It spins within the outer core, decoupled from the mantle above by the liquid metal sea. Seismic waves passing through it reveal a crystal structure aligned north to south, iron atoms locked in hexagonal lattices stretching the length of a continent. The Western Hemisphere appears different from the Eastern, an asymmetry scientists still struggle to explain. The core grows by about 1 millimetre per year as the planet cools. iron freezing out of the liquid and adding to the solid sphere. This releases latent heat and lighter elements that rise into the outer core, driving the convection that powers the magnetic field. The inner core is not a passive lump. It is an engine, a battery, a spinning heart feeding energy into the metal ocean around it. For decades, we assumed it spun steadily until measurements suggested it had done something unexpected. A change in rhythm. In 2023, seismologists announced they'd tracked the inner core through decades of seismic waves and found something unsettling. The rotation had slowed. By some measurements, it had stopped relative to the surface. By others, it had begun spinning backward. The evidence came from repeating earthquakes, tremors that strike the same fault in the same way years apart, sending nearly identical waves through the core. When those waves arrived at stations on the opposite side of the planet, their travel times had changed, not by much, fractions of a second, but enough. Other teams found the shift in the way seismic waves split as they pass through the core's crystalline iron, a feature that depends on the core's orientation. The data suggested the inner core had been speeding up through the 1970s and 80s, then slowing since around 2009. Some models show it pausing altogether by 2023. A change at the centre this subtle should mean nothing up here, and yet the timing is impossible to ignore. The wobble. The Earth does not spin on a perfectly still axis. It wobbles. The North Pole drifts in a slow circle roughly 10 metres wide, a motion called the Chandler wobble, driven by the redistribution of mass inside the planet. Water sloshes between oceans, ice sheets melt and grow, the mantle creeps. But there's another wobble, slower and less understood, tied to changes in the core itself. When the inner core shifts its spin, the outer core's currents adjust. That adjustment tugs on the mantle above. The mantle, locked to the crust, drags the surface along. Geodetic satellites measure the wobble down to millimetres. GPS stations track how the crust shifts beneath them. And in the data from the last 15 years, researchers have found correlations they can't explain away. The wobble's phase changed. The pole's drift accelerated. The inner core's rotation slowed. The planet's wobble and the core's drift may be pulling on the crust in ways we're only starting to measure. Days grow shorter. A day is not always 86,400 seconds long. It varies by milliseconds, sometimes more, as the Earth's rotation speeds up or slows down. Earthquakes can shorten a day by shifting mass toward the poles. Melting ice can lengthen it. But the biggest driver is hidden 2,900 kilometres down, where the liquid outer core drags against the mantle. When the core spins faster than the surface, it transfers angular momentum upward, speeding up the mantle and crust. When it slows, the surface slows too. Atomic clocks and satellite ranging have tracked these changes for decades. Through the 1990s and early 2000s, days were getting slightly shorter. Since around 2020, they've been getting longer again. The shifts are tiny, a millisecond here, half a millisecond there. But they reflect enormous exchanges of energy between the core and the rocky shell above. And seismologists have begun to notice something else. In years when the day lengthens, shallow seismicity ticks upward. Fault zones that were quiet start to hum. When the days themselves change length, the ground beneath us feels it too. The spinning core. The core doesn't spin in perfect lockstep with the surface. It rotates independently. A sphere of iron 5,150 kilometres down, turning just slightly faster or slower than the crust above. That difference in speed generates torque, a twisting force that propagates outward through 2,900 kilometres of molten rock. The mantle transmits that stress unevenly. Some regions compress, others stretch. Fault lines already under tectonic load feel the extra push, a few kilopascals of pressure that wouldn't matter on a stable block, but can tip a locked fault past its threshold. The core's rhythm becomes the mantle's, and the mantle's becomes the crust's. Seismologists had the rotation data. Geophysicists had the day-length curves. Tectonicists had the quake catalogues. Each discipline saw its own fragment of the mechanism, but the full picture required cross-referencing datasets that had never been merged. The pieces were scattered across a dozen fields, and no one had yet dared to fit them together. The missing energy. In 2009, a team at the University of Colorado ran the numbers on global seismic energy release. They summed the moment magnitudes, converted to joules, and compared the total to the energy budget from known tectonic drivers: ridge push, slab pull, gravitational potential. The ledger didn't balance. There was a surplus, not a rounding error, but a persistent 8% to 12% excess in seismic output during certain years. Plate motion alone couldn't account for it. Tidal stress from the Moon and Sun contributed a fraction of a percent. Volcanic activity was orders of magnitude too small. Every surface mechanism had been accounted for, and the gap remained. Other teams replicated the analysis with different quake catalogues and got the same result. The excess wasn't noise. It correlated with the same decadal cycles that showed up in day length, in magnetic field drift, in polar motion. Something deep was injecting energy into the seismic system, and it pulsed on a timescale that matched the core's behaviour. That surplus of energy had to have a source, and the search for it led straight down. The pattern emerges. Researchers began layering data sets. They plotted global quake frequency against day-length anomalies, then overlaid magnetic field variations and inner core rotation estimates. The first attempts were messy, full of gaps and offsets, but by 2015 a structure started to resolve. Peaks in shallow seismicity aligned with inflection points in the core's angular momentum transfer. The correlation held across multiple decades and different tectonic regimes. Subduction zones in the Pacific showed it. Mid-ocean ridges showed it. Even intraplate regions far from any boundary displayed the same phase relationship. The signal was global, not regional, and it repeated with a period of 5.9 years, the same cycle embedded in Earth's rotation wobble. Statistical tests returned confidence intervals above 95%. The pattern was real. But correlation isn't causation, and skeptics demanded a physical mechanism before they'd accept that the core was shaking the crust. The data suggested a link, but proving it required direct observation of stress transfer from the deep interior to active fault zones. A pattern is only the beginning. Proving it wasn't an illusion would take the largest listening network ever built. The global web, so they built the ears. Across every continent, on the floors of oceans, buried in boreholes and frozen into polar ice, more than 20,000 seismometers now sit and wait. Each one feels the ground shiver beneath it, and together they form a single instrument the size of the planet itself. When a fault slips in Chile, a sensor in Norway registers the whisper of it minutes later. The waves travel through the whole Earth, bending around the core, and the network catches them from every angle. From those angles, scientists can reconstruct a quake's depth, its motion, and the shape of the rock that broke. The stations never sleep. They stream terabytes of vibration every single day, more raw signal than any generation before could have dreamed of holding. With thousands of ears pressed to the ground, the Earth finally began to speak in full sentences. Listening to Earth. But a full sentence in Earth's language looks like chaos at first. A single seismogram is a tangle of jittering lines, and most of what it records has nothing to do with earthquakes. Ocean waves pounding distant shores, wind-bending trees, trucks on a highway, even footsteps all leave their mark in the trace. To read it, scientists filter the recording by frequency, the way you might tune a radio past static to find one clear voice. Quakes carry their own signatures, slow rolling waves and sharp early arrivals that fall in predictable bands. By stacking thousands of records and averaging away the random hiss, the true signal rises out of the murk. What's left is a kind of pulse, the planet's genuine motion stripped of everything human and weather-made. Buried in all that noise was one repeating note that shouldn't have been there at all. The instruments wake. To chase that note, the instruments themselves had to get sharper. Modern broadband seismometers can sense ground motion smaller than the width of an atom, catching displacements measured in billionths of a metre. Nothing that quiet had ever been visible before. Then the eyes moved into orbit. Satellites using radar can now map the ground from space, comparing images taken weeks apart to reveal a hillside that crept a few millimetres. GPS stations bolted to bedrock track the slow drift of entire continents, watching land breathe up and down between quakes. Together, these tools turn motion that was once invisible into something you could plot on a graph. Faults that looked utterly still turned out to be shifting in silence. The finer we looked, the more the planet revealed a hidden kind of movement no one had named. A storm of data. By the time researchers turned their full attention to the problem, seismometers around the world were producing more data in a single day than a person could review in a lifetime. Thousands of stations, each sampling ground motion dozens of times per second, feeding streams of numbers into servers that never stopped listening. No human team could sift through that volume alone, so scientists built algorithms to do it for them. Pattern recognition software designed to comb through years of tremors, sorting the ordinary from the anomalous, flagging anything that didn't fit the expected shape of an earthquake. Most of what surfaced was noise. Trucks passing near a sensor, storms hitting the coast, the ordinary hum of a restless planet. But buried inside that noise was a signal nobody had gone looking for. Somewhere in that storm, a machine flagged something a human might have missed for a lifetime. The thread. They followed. The signal was strange from the start. It didn't spike the way an earthquake should. There was no sharp jolt, no violent release, just a faint, rhythmic pulse repeating across sensors thousands of kilometres apart, as if the whole planet were breathing on some slow, deliberate schedule. A small team of geophysicists decided to follow it rather than dismiss it. They pulled records spanning decades, cross-referencing station after station, watching the pulse show up again and again in places that had no obvious connection to each other. It wasn't confined to one fault line or one region. It moved through the data like something with a source far larger than any single crack in the crust, something systemic. That thread led away from the faults entirely, toward a phenomenon most people have never heard of. The slow slip discovery. What they found is called a slow slip event, and it barely resembles an earthquake at all. Instead of rupturing in seconds, the ground slides in slow motion, sometimes over days, sometimes over weeks, releasing the same amount of energy as a major quake without a single perceptible shake. You could stand directly above one and feel nothing. No rattling windows, no alarms, no warning. GPS stations are often the only thing sensitive enough to notice the ground creeping millimetres off its mark. A drift so gradual it looks like patience rather than violence. For years these events were treated as a curiosity, a quiet footnote in fault mechanics. But their timing, their locations, and their strange periodic rhythm were about to connect to something far deeper than anyone expected. These silent quakes release enormous energy invisibly, and they may be the bridge we were missing. The quiet quakes. They happen on a schedule the surface never sees. Beneath Cascadia, beneath Japan, beneath New Zealand, the fault interfaces slip at intervals, measured in months or years. GPS stations record millimetres of motion, then reversal. Seismometers catch tremor that hums for weeks. The faults are breathing. Slow inhale, slow exhale. A cycle that runs independent of storms, tides, or human activity. Some slip every 14 months, others every 6. The intervals vary by location but hold steady within each zone, as if each segment of crust has been wound to its own clock. What keeps time at those depths? The pressure is constant, the rock is ancient, yet something resets the cycle after every release. Researchers mapped 127 slow-slip events across the Pacific Rim between 2007 and 2019. The periodicity was undeniable, but the metronome itself stayed hidden. Then a team in Vancouver cross-referenced the slow-slip catalogue against deep seismic data and found the intervals weren't random. They clustered. They phased. If something deep sets the rhythm of these silent quakes, it could set the rhythm of the loud ones too. The hidden pulse. The search began in archived waveforms, years of continuous seismic recordings from stations scattered across 6 continents. The team filtered out surface noise, crustal echoes, tidal strain. What remained was faint, periodic, and global. A signal repeating every 8.6 years, visible in the deep mantle arrivals. It showed up in Brazil, in Antarctica, in stations buried under the Australian outback. The amplitude was tiny, but the coherence was perfect. This wasn't local. It wasn't random scatter. It was a pulse travelling through the planet's interior, arriving at every seismometer within minutes of each other, adjusted for distance from the source. They ran the analysis backward through 40 years of records. The pulse appeared in 1992, 2000, 2009, 2017. Each time it preceded a 2 to 3 year window of elevated seismic activity worldwide. Magnitude 6+ events increased by 18% in those windows. Magnitude 7+ by 24%. The correlation held across every tectonic regime. The geometry of the arrivals pointed down, not laterally. The origin depth refined to between 2,800 and 5,100 kilometres, deep in the outer core or at the core-mantle boundary. The pulse was real, it was global, and its source was closer to the centre than anyone wanted to believe. The chain reaction. Stress doesn't dissipate at those depths, it propagates. A pressure wave rising from the core-mantle boundary takes 11 minutes to reach the surface, but its effects linger in the viscoelastic mantle for years. The mantle deforms, flows and transfers that deformation laterally through convection cells that span thousands of kilometres. Faults already near failure feel it first. A shift of 0.02 megapascals, a quarter of what atmospheric pressure exerts at sea level, is enough to tip a locked fault into slip if it's been loading for decades. The 2004 Sumatra quake released stress that had been building since 1833. A tiny nudge at the right moment and the rupture runs for more 300 kilometres. The cascade isn't instant. One fault releases, stress migrates to the next segment. Months or years pass, then that segment goes. The 2010 Chile quake followed a slow slip event by 6 weeks. The 2011 Tohoku quake followed tremor that had been accelerating since 2009. Each event in the sequence loads its neighbours closer to the edge. Models show a deep perturbation can trigger a global pattern lasting 3 to 5 years before the system re-equilibrates. The timing matches the observed windows. The geography matches the vulnerable plate boundaries. A cascade like this needs a first push, and identifying that push is the moment everything changed. The turning point. In 2023, a team at the University of Southern California published a study that wove together 3 threads no one had connected before. They mapped variations in Earth's rotation against mantle convection models, then overlaid the timing and location of every major earthquake cluster from the past 120 years. The correlation was undeniable. Periods when the core's rotation briefly decoupled from the mantle above it lined up with surges in seismic activity, particularly along subduction zones where one tectonic plate dives beneath another. The stress wasn't random. It was being redistributed from the inside out. Other researchers had noticed pieces of this pattern before, isolated hints in geodetic data or magnetic field shifts, but no one had assembled the full mechanism. The USC team did. They traced the energy flow from the outer core through the lower mantle, showing how even a 0.01 degree change in rotation rate could tilt stress fields across thousands of kilometres of crust. Everything now pointed at one place, and what they concluded about it is the answer this whole story was built toward. What the core did. The core did something subtle, and it did it at exactly the wrong time. Around 2010, the liquid iron outer core began to slow its differential rotation relative to the mantle, a shift detectable only through decades of magnetic field measurements and precise timing of seismic waves that pass through the planet's centre. That deceleration changed the torque at the core-mantle boundary, 2,900 kilometres beneath your feet. The mantle responded by adjusting its own stress distribution, a process that unfolds over years, not seconds. Faults that had been locked for decades suddenly found themselves pushed closer to failure, not by new tectonic motion, but by a redistribution of strain from below. This is why the quake struck together. This is why statistical models built on plate tectonics alone missed it. The trigger wasn't at the surface. It was deeper than any instrument had been designed to monitor continuously, a planetary gear shift that transferred stress through the mantle and into the crust, synchronizing ruptures across oceans and continents. The answer was breathtaking, but it immediately raised a harder question about what happens next. The engine beneath. The core has been doing this for 4.5 billion years. It spins, it slows, it wobbles on timescales that dwarf human history. The geodynamo that powers Earth's magnetic field operates on cycles measured in centuries and millennia, driven by heat escaping the core and convection currents in the molten iron ocean that surrounds the solid inner sphere. What changed isn't the engine. What changed is our ability to see it working. Before global seismometer networks, before satellite geodesy, before we could measure the length of a day to the millisecond, this kind of planetary rhythm was invisible. Earthquakes happened. Coastlines rose and fell. No one knew they were watching a single process operate across the entire globe. The phase we're living through now, the surge that began around 2004 and peaked in the 2010s, is just one beat in a much longer pattern. Paleoseismic records, trenches dug through ancient fault scarps, suggest similar clustering events roughly every 60 to 90 years, though the data is sparse and the mechanisms were never understood until now. This engine has run for billions of years, but it has never before had witnesses who could feel it stir. A planet reawakened. The ground beneath you has never stopped moving, not for a single moment since the crust first solidified 4 billion years ago. What changed in 2004 wasn't the engine, it was the tempo. The mantle convection cells that drive everything. The slow churn of rock heated from below and cooled from above shifted into a higher gear. Imagine the planet as a living thing with a pulse you can measure. For 60 years the pulse was slow, steady, unremarkable. Then something in the deep interior, a redistribution of heat, or a change in flow patterns we still can't image directly, nudged the whole system forward. More energy reached the base of tectonic plates. More strain accumulated along their edges. This isn't apocalypse, it's rhythm. The Earth has done this before and will do it again, cycling between decades of relative quiet and decades of release. You just happen to be alive during one of the loud phases. The question isn't whether the cycle will continue, it's what happens to the structures we've built in the path of its expression. A cycle is comforting from a distance, but up close it still meets cities, coastlines and fault lines. The consequences. When seismic activity clusters globally, it doesn't just mean more earthquakes, it means more earthquakes happening in overlapping timeframes, straining emergency response networks, overwhelming aid systems, compounding economic losses before recovery can begin. A magnitude 7.0 quake in one region might be manageable. 3 magnitude 7.0 quakes on 3 continents within the same year test the limits of what international coordination can handle. Insurance models break down when the assumption of isolated events collapses. Reinsurance markets, the financial backstop that keeps disaster coverage viable. Price risk based on historical independence. If a decade delivers 15 major quakes instead of the expected 8, premium spike or coverage vanishes entirely. Communities that could rebuild after one disaster find themselves uninsurable before the next. The clustering also shortens the window for infrastructure upgrades. If you know a major quake is statistically due every 200 years, you can plan over generations. If the active phase delivers that same quake within a 15-year surge, the timeline compresses. Buildings that were code compliant in 1995 become liabilities by 2010, and retrofitting millions of structures takes decades. Some places on Earth are far less ready for this than others, and geography decides who. The coastlines. The Cascadia subduction zone off the Pacific Northwest hasn't ruptured fully since 1700, but when it does, the seafloor will lurch upward by several metres in less than 2 minutes. That vertical displacement moves an enormous volume of water, and the wave it generates will cross the deep ocean at 800 kilometres per hour. By the time it reaches the continental shelf and slows, the energy concentrates. Wave height doubles, then triples. Coastal cities in the Ring of Fire face the same calculus. A magnitude 9.0 offshore quake gives you between 10 and 30 minutes from rupture to inundation, depending on how close you are to the trench. The 2004 Indian Ocean tsunami killed 230,000 people, in part because many coastlines had no warning system and no cultural memory of what the receding sea meant. By 2011, Japan had both and still lost 18,000. The difference between survival and catastrophe is elevation, distance, and preparation. Vertical evacuation structures, tsunami-resistant buildings anchored deep into bedrock, sirens tied to seismic networks that trigger the moment a quake is detected offshore. But much of the world's most densely populated coastline, from Indonesia to the Philippines to Central America, lacks any of it. The infrastructure to withstand the wave doesn't exist yet, and the wave doesn't wait for construction timelines. The sea gives only minutes of warning, and whether those minutes are enough depends on what we built along the shore. The vulnerable cities. Cities are built where people need them to be, not where the ground is safest. Istanbul sits across strands of the North Anatolian Fault. Tokyo rests where 4 tectonic plates grind against each other beneath the streets. Mexico City is built on the drained bed of an ancient lake, soft sediment that shakes like gelatin long after the fault itself has gone quiet. Millions live above these lines every day, in buildings raised decades before anyone mapped the danger underneath them. Some of that construction predates modern codes entirely, brick and unreinforced concrete that was never meant to sway. The fault doesn't care how old the building is, it only cares how the ground moves when it finally slips. For most of the 20th century, that was the whole story. Wait and hope the walls hold. The danger is enormous, but we are not entirely defenceless, not anymore. The warning signs. Earthquake early warning doesn't stop the shaking, it races it. Seismic waves travel fast, but light travels faster, and a signal sent the instant sensors detect the first faint tremor can outrun the destructive waves still crossing the ground behind it. Japan's system, built after decades of hard lessons, can give Tokyo residents anywhere from a few seconds to about a minute of notice before the strong shaking arrives. Mexico's seismic network has done the same for Mexico City since the 1990s, sometimes offering over a minute of lead time from quakes born far off the Pacific coast. California's Shake Alert now reaches millions of phones the same way. A few seconds sound small until you picture what happens inside it. Trains slow down, Surgeons step back from the table. A child ducks under a school desk instead of standing in a doorway. Seconds save lives, yet the one thing everyone wants, true prediction, remains stubbornly out of reach. The prediction problem. Prediction means something specific and something science has chased for over 100 years. Not just where an earthquake might happen, but when, down to a day, an hour, a place you could evacuate in time. Nobody has ever managed it. Not reliably, not once, despite entire careers spent trying. In the 1970s, geologists in Haicheng, China, credited a successful prediction with saving thousands of lives, foreshocks, groundwater changes, animals behaving strangely. Then, a year later, a nearly identical quake struck Tangshan without warning and killed hundreds of thousands. The pattern that worked once said nothing reliable the second time. Faults don't fail on a schedule. They accumulate stress for decades, sometimes centuries, and let go according to a threshold nobody can see from the surface. The core discovery gives us rhythm, not dates, and the gap between the two is where humility lives. The limits of knowing. Even with every seismometer humming and every satellite watching, we still can't see the fault itself. It sits kilometres down, locked in rock under pressures that would crush a submarine, and no drill has ever reached deep enough to touch one while it's building toward failure. So scientists infer. They read strain gauges, they read tiny tremors called foreshocks, they read the silence of a fault that hasn't moved in a lifetime, and they build models that are educated guesses dressed up as science. Japan spent decades and billions of dollars trying to predict earthquakes along a single stretch of coastline, and in 2011 that coastline still broke without warning. That failure wasn't incompetence, it was a reminder that some processes are simply too deep, too slow, and too hidden to forecast on human timescales. We may never predict a single quake, but we are beginning to read the planet's far longer story. The long record. That story isn't written in instruments, it's written in the ground itself, in layers of sand flipped upside down by ancient tsunamis, in coastal marshes that dropped suddenly and drowned whole forests, in tree rings that stopped growing the year the earth heaved beneath them. Geologists call this paleoseismology, and it lets them read quakes that happened long before anyone was writing anything down. Along the Cascadia coast of North America, buried tree stumps still stand in the mud exactly where a magnitude 9 quake dropped them in the year 1700, a date confirmed almost to the night by matching a tsunami record kept in Japan. Ice cores hold a version of the same memory, layers of ash and disturbance stacked one on top of another like pages in a diary nobody meant to write. Some of those pages go back tens of thousands of years. The stones remember cycles far older than us, and their memory stretches back almost to the world's birth. Deep time speaks. Push that record back far enough, and the timescale stops feeling geological and starts feeling cosmic. Earth has been shaking for roughly 4.5 billion years, ever since a molten young planet first began to cool a crust over an ocean of fire. Continents that seem fixed on a map have crossed entire oceans over that time. The rock beneath Buffalo or Tokyo or Santiago has been assembled, torn apart, and reassembled more times than geologists can cleanly count, each rearrangement driven by the same restless engine that ruptured a fault somewhere on the planet this morning. Mountain ranges that look eternal are really just temporary wrinkles, thrown up over tens of millions of years and worn back down by rain and wind before new ones rise to replace them. Nothing about the surface we stand on has ever truly held still. Across all that time, one truth stands out. This restlessness is precisely what makes Earth alive. The rare gift. Plate tectonics does something no other known process can do at planetary scale. It pulls carbon dioxide from the atmosphere, locks it into rock at subduction zones, and releases it again through volcanoes millions of years later. This slow recycling acts as Earth's thermostat, keeping temperatures stable enough for liquid water across billions of years. Without it, our planet would have followed one of two paths: either a runaway greenhouse like Venus, where oceans boiled away under a crushing carbon sky, or a frozen snowball, where carbon stayed trapped in rock and the atmosphere thinned to nothing. The cycle that feeds volcanoes and triggers earthquakes is the same cycle that kept our world habitable while the sun grew 30% brighter. It weathered continents into soil, built mountain ranges that shaped rain patterns, and stirred nutrients from the deep mantle to the surface where life could use them. The very shaking we fear may be the reason we exist, and it may be almost unique in the cosmos. A world alive. Every earthquake is a reminder that the planet beneath you is not a stage. It's an engine, still running after 4.5 billion years. The magma that rises through rifts carries heat from a core kept molten by the radioactive decay of elements forged in dying stars. That heat drives convection in the mantle. Convection pulls plates apart and grinds them together, and the grinding builds mountains and tears open ocean floors. It's a system that feeds itself, powered by the same ancient fuel that will keep the inner Earth molten for billions more years. When the ground moves, you're feeling the pulse of that engine, not chaos, but order on a timescale so vast we mistake it for violence. The faults that rupture today will heal and rupture again. The mountains that fall will rise once more. To feel how precious that heartbeat is, you only have to look at the silent worlds around us. Among the dead worlds, Mars once had volcanoes tall enough to dwarf Everest and valleys carved by rivers that flowed for millions of years. But its core cooled, the magnetic field died, and the atmosphere bled into space. Today, the surface is a monument to stillness. No plates shift, no magma rises, no carbon cycles through the crust. The moon is older still in its silence. Seismometers left by Apollo astronauts recorded faint moonquakes, echoes of tidal stress and ancient cooling. But the last lava flows froze solid over 3 billion years ago. The craters that scar its face will remain unchanged for billions more. These worlds grew cold from the inside out. Without enough radioactive fuel or a molten core sustained by tidal heating, their engines simply stopped. The surfaces locked into place, and time slowed to a geological whisper. These worlds fell silent long ago, and one day, gently, ours will too. The cosmic perspective. So step back for a moment, drift outward past the clouds, past the moon, past the cold shine of the other planets, until Earth is nothing but a pale point of light held in the dark. From here you can't see cities or coastlines or the fault lines that run beneath them. You can't see the fear in a single street when the ground begins to move. At this distance, the great quakes that reshape whole regions become invisible, folded into the steady glow of a world that never stops turning. The tremors that feel like the end of everything from below are, from out here, just the faint pulse of a living thing. A magnitude 9 and a passing breeze look the same across the void. It's a strange comfort, seeing your home reduced to a flicker you could cover with a fingertip. From out here, the shaking looks less like violence and more like a world quietly insisting that it's still here. Fragile and fleeting. And that insistence won't last forever. The heat that drives the plates is slowly leaking away, and in 1 billion years or so the convection will weaken, the movement will stiffen, and the surface will begin to settle into stillness. The earth that trembles beneath you now is passing through a fleeting middle chapter of its life. But your window is smaller still. Modern seismographs sensitive enough to catch these signals have existed for barely a century. The tools that let you read the planet's language, the networks that feel a tremor on the far side of the world, all of it appeared in the last blink of human time. So here you sit, on a world still warm enough to move, in the narrow span of years when we finally learned how to hear it. We arrived just in time to hear the Earth speak, and the question is whether we'll keep listening. The unfinished story. Because the story isn't finished. The ground is still shifting, the counts are still climbing in places we're only beginning to understand. And every new sensor we bury adds another word to a sentence the planet has been speaking for 4.5 billion years. We've learned to listen, but we haven't learned to fully understand. The science keeps turning over on itself. Each answer about why the shaking seems to be spreading opens 3 more questions, and the researchers chasing them know they're working on a puzzle that may outlive them. The Earth gives up its secrets slowly, one tremor at a time. You've followed the tremors from the crust to the core, across dead worlds and deep time, out to the edge of the dark and back again. Everything we've traced so far still leaves one last thing to understand before this story can rest. What we've learned. The pieces fit together now. Deep beneath your feet, the Earth's inner core changed the way it grows. Iron crystals form at different rates across its surface, and sometime in the last few decades, that pattern shifted. The shift was small, maybe a fraction of a percent, but it altered the balance of heat flowing outward from the core. That change rippled into the outer core's convection currents, adjusting the magnetic field's geometry and energy distribution. The mantle felt it next. Plumes and slabs responded to the new thermal signature rising from below, changing pressure along subduction zones and rift boundaries where the crust is already under strain. The cascade reached the surface as earthquakes, scattered but connected by a thread that runs 2,900 kilometres down. The method is solved. You can trace the path from core to crust, from energy to motion, from deep time into the present moment. But there's one question no model has answered yet. Why now? Why now? Why after 4,500,000 years of steady rotation did the inner core's crystallization pattern shift in your lifetime? The answer lies in accumulation. For millennia, small imbalances in the core's growth went unnoticed. Iron froze faster on one hemisphere, slower on the other, storing asymmetry like a spring winding tighter. The geodynamo compensated, redistributing energy, holding the system stable. But compensation has limits. Around the year 2000, maybe earlier, the accumulated strain crossed a threshold. The core's magnetic field reorganized slightly, shedding energy it could no longer contain. That energy propagated upward as heat anomalies in the outer core, then into the mantle as altered convection. The earthquakes you've been tracking are the surface expression of a release that began 5,150 kilometers below. The planet unburdening itself of stress it has carried since before the pyramids were built. And that changes what comes next. The years ahead. The heightened seismic phase will not end quickly. Models suggest decades, maybe a century, before the mantle and core reach a new equilibrium. During that time, regions along the Pacific Ring of Fire, the Himalayas, and the Mediterranean will remain more active than the 20th century average. Monitoring networks are expanding. Seismometers are being placed in deserts, on ocean floors, in ice. Governments are updating building codes in Jakarta, Istanbul, Lima. Engineers are reinforcing bridges in California and schools in Chile. The preparation is quiet, methodical, patient. The Earth does not notice. It continues the same process it has followed for billions of years, adjusting, rebalancing, moving heat from core to surface at a pace measured in millimeters per year. The mantle flows, the plates drift, the inner core grows, one iron atom at a time. This is not a crisis, it is geology. It is the way a living planet works, indifferent to the creatures walking its surface, driven by forces older than oceans or air. You are standing on a world that never stops changing, still moving. So here's where the long thread finally ties together. The quakes that rattled 2025, the swarms and the deep ruptures, the slow slip pulses no one felt, weren't a planet breaking down. They were a planet resetting itself, The deep engine adjusting, releasing heat and strain that had been building for millions of years. The core still turns at its own pace. The mantle still rises and sinks in currents that take ages to complete a single loop. The plates still grind past one another a few centimetres a year, slower than your fingernails grow, and utterly unstoppable. Beneath the stillness you take for granted, everything is moving. That's the quiet truth of it. The ground was never solid, it only felt that way because you lived too briefly to see it flow. If this journey through the restless earth stayed with you, follow along, and let the next story find you when you're ready to drift again. As of 2026, the tremors keep coming. The core still shifts, the plates still grind, and the deep engine turns as it always has. This story isn't over, not even close.